Thank you, Paul. I'm really happy to be here. We have a couple other folks from Akamai, our architect Owen here, and also Maritz is with us. What I'm going to talk to you about today is hopefully something that's quite a bit different than everything else. Not that those weren't good, but I want to show you just a different way to think about IPv6 than just about deployments and things. We're going to deep dive into the way IPv6 addresses look and how much more complicated, not dauntingly complicated, but how much more complicated or differently complicated v6 is than what you might have been used to with v4. So I'm calling it an Akamai view of global IPv6 addressing. And in my role as a scientist at Akamai, I'm in a curious group called Custom Analytics. We use the platform as a measurement instrument. We use it as a telescope on the entire internet. So, I'm not involved with the other products proper, but what we do is custom research for customers that are interested in what you can see from that vantage. I pushed the wrong button, excuse me a sec. Okay, so what we're going to go through today is first why network engineers, operators, analysts, developers, anyone here, why you care about v6 in terms of operational things. And then I'll go through a quick introduction to IPv6 addresses. I know a lot of you know these things, but I'm going to talk about the way we look at them visually and classify them, and then how we can automate that. So it won't be completely redundant if you're intimately familiar with it already, and it'll be eye-opening if you're not familiar with it. Then we'll talk about the notion of IPv6. We'll talk about the ways we measure v6. How do we measure the growth? And I'm measuring it differently than other people are measuring it, so you'll get a different perspective on it. Then we'll talk about IPv6 address classification. In v4 addresses, well, at least we're very used to them. We don't actually think of classifying them. Any one is as good as another. But we'll talk about IPv6 offers a lot more freedom there, and so you can have different kinds of addresses. And specifically, we'll talk about temporal and spatial classification. How do the addresses exist over time, and where do they exist in this vast address space? And then we'll go into a visualization. I'll show you a visualization of the whole v6 internet from our perspective, from World Wide Web clients on v6 touching our platform. And then, if time permitting, I'll show you the latest stuff we're doing with abuse mitigation or threat mitigation in the v6 space by deeply understanding those addresses. And then we'll wrap up with some takeaways. So some of this was said before, but to reiterate, IPv6, it's production quality now, and it will operate simultaneously with v4 for the foreseeable future. I think for a lot of the rest of our working careers, they're both going to be around. It's optimistic, and I don't disagree that maybe v4 would be awesome if it went away at some point, but I don't see that happening. So for the time being, we have one internet, and there's two protocol versions, and they share a lot of rendezvous mechanisms. A lot of people like to say when they're teaching about v6 that they're two separate internets. That's a very useful concept in terms of teaching, but remember that we have rendezvous mechanisms at the application level that happened before that, and those things are choosing to use one protocol or the other. Well, why should we care about this? Well, we care because IPv6, at least in Akamai, it changes the way IP geolocation works. A lot of things in the v4 internet, we think we know where they are. We might restrict content based on the country that we think someone's in. That's hard to do with a new addressing scheme. It changes client reputation. Because we have things like privacy addresses and ephemeral addressing, is client reputation, how long does it last? What's going on there? At what prefix length does a client even exist? It changes threat mitigation because if you find something happening on your platform, like say some sort of abuse or attack, at what level would you block that? Do you block it at /64? Do you block it at 128? Do you block it at /40? What exactly is the entity that you're trying to constrain on the other side? And then it changes things like those processes and those tools that we have. It changes log processing. It certainly changes privacy because you can have addresses that are they have random numbers and then they're meaning to hide your identity or at least make you not trackable. And it changes things like real user monitoring. In the web, very often we push JavaScript code down to the client and we use that to get real feedback about how it's performing. Well, if you're on v6 and you have another address through dual home, you can get different performance in different places. And these identifiers are bigger. Their logs just look different. So IPv6 addresses look a lot of different ways, and that's because there's a lot of different ways you can form them. But largely what we do is, the recommendation is to cleave them into two parts, the top 64 bits and the bottom 64 bits. And here I've highlighted the bottom 64 bits. You call that the interface identifier. The network identifier is up top. In v4, we had the same thing, the host identifier and the network identifier. Now, if we take those and bloat them up, because as Paul pointed out, or I think it was Paul pointed out earlier, you have the same address, and it can look a lot of different ways. So if we change from this presentation format into something that's predictable, like a fixed width format, where I put all the zeros back in, now we have this matrix of values. And someone who is an IPv6 expert can eyeball these and tell you some things about them. For instance, in that first of the 4 addresses, I see FFFE in that particular position. I've highlighted it here in red. That's a signal that it's usually a modified I64 address, and the lower part of the address is based on the Ethernet MAC address underneath. The next address, which I highlighted blue and colon 103, it's a low number down there. There's a big string of zeros, so we sometimes call these low byte addresses. It suggests that these are hand numbered the same way we would have like a .103 or something like that in a v4 network. The third address has, in 2 colon segments, 2 different numbers. It could be one big low number, 100911, or it could be something like a subnet, the 10 subnet, and then 901 being the host. So, but it looks hand numbered the way you would maybe in a DHCP pool or a static address. And then the last one is the most common kind of IPv6 address, the ephemeral privacy address. The Slack standard stateless address auto configuration, the client picks up a random number and you put them there. Over 90% of the addresses that we see touch the platform are addresses of that variety. So we can classify these addresses just by eyeballing with some level of confidence. Now, clearly, that thing that I just went through, it's not magic. It could be automated. And here's a tool, a freely available tool by Fernando Gant called Adder6 that can do that classification. I just took those 4 addresses and pumped them into Adder6 and said, can you classify these for me? And it said, oh, I see you've got 4 unicast addresses. They're globally routable. One's IEEE based, that one modified US64 I talked about. One looks like it might be randomized, although it's nearly impossible, practically impossible to determine if a number is random, especially standalone. And it says 2 of those low byte addresses I talked about. So you can automate that kind of classification. Now in this talk, we're going to talk about this class of addresses that I call here World Wide Web client addresses, probably the largest pool of IP addresses of either protocol version. There are other kinds of addresses, certainly the ones that services operate on, that you pin up on your servers. There are router and transit addresses. And here's a Venn diagram of those types, and they can be shared, right? You could imagine, for instance, a NAT router is a router. It also runs a service. It might have a web interface on it, and it's also a client when you're talking about it from a remote point of view. We're going to focus on the leftmost ones because the Akamai platform is unique in that it can see probably most of those in the world, but the other classes we're not. We are also able to see those, but you can see those as well. You can use passive DNS to look for the server addresses, and you can do trace routes to discover router addresses. So these are generally the classes we're talking about, and sometimes they're of multiple kinds. So how do people measure v6? I think we saw a plot like this from Paul earlier about from Facebook. The proportion of clients that come to a service, do they choose to use v6 or not? So this is this happy eyeballs implementation in the client that's choosing whether or not it would like to use v6. And we're running 10, 11, 12% of web clients that access Google properties, or I think Facebook as well. About 10 or 11% of those will choose to use v6. So that's a good measure of about 10% clearly have v6 for web clients. This data, by the way, is not mine. It's from Google, and it's up on the web. Now, we measure it differently. That's based on sampling or based on looking at the kinds of transactions that come there. What I do instead is I count the addresses, the unique addresses that come to our platform at every possible prefix length. And I'll show you what that means. But basically what we see is about 500 million unique IPv6 client addresses per day, about 10 billion per month. If you compare that to IPv4, we might see 600 to 800 million a day, 900 million in, say, a week or a month, and more than that in a year's time. And per month, so probably 900 million a month in IPv4. So we're well beyond, in terms of raw addresses, the number we see in v6 clients, even though there appears to be only about 10% deployment in the world. So when I count those addresses now in time series over the past 2 years, on the far left is March 2014 to March 2016 on the right, this is the growth that we see. So the most prominent one, that blue line on the top, that's raw full v6 addresses. Unique v6 addresses counted every 6 months at those dots in the graph. So we were seeing for the first year and a half about a doubling every year, about a doubling every year. So and then a little bit of change towards the end here that looks like it might be leveling off a bit. But remember that we're using the Akamai platform as the measurement instrument, so its lens could be blurred in some way. I mean, we don't know if we're seeing all the deployments. We're seeing certainly things that come to Akamai properties. This is, by the way, in a day. So most recently, we saw 513 million in a day in the middle of March. And now if we count, I said I count them at every possible prefix length. Well, that's the full /128 bits. What about at the /64? Because we know that's used for special purposes. Well, that next line that's shown in purple here in cyan, overlaid with it, is the 163 million. That's the number of unique /64s we see in a single day. Okay? And some people think that that might be a good approximation of the real number of hosts that are using v6. And that would be the case if they were using straight up Slack and they didn't change their address more than once a day and they weren't doing anything funny in the subnet identifier. We'll explore what some of that is. The other thing is I want to show you, I guess, to dispel a little myth. Some people still think, not necessarily here, but some people in the world think that the transition technologies are still very commonly used. IPv6 tunneling like 6 to 4. All these other categories, these other colors down there, they're all down in the weeds and they're almost inconsequential. So the native traffic is what we're counting in those lines at the top. That's really good news if you're a v6 proponent. Now let's take those counts and count them, instead of daily, let's count them weekly. Now in something like v4, this wouldn't change very much, right? Because you don't have classes of addresses that are ephemeral. But in v6, we do. So when you count the number of unique addresses over a week's time, we have 2.82 billion in a week. So if you're thinking about dimensioning storage for them, if you're logging things, whatever, this is a lot. The data structures are bigger. You have to start rethinking the way you're going to handle things because you can't even have that many v4 addresses unicast. There are just not that many used on the internet today. And then in a week's time, now counting the /64s, remember we're kind of thinking of this as a candidate estimate of how many hosts in the world might have v6 service. We get 438 million. So what you're seeing is you think of the Akamai platform, over time, more people will come to our properties. Maybe somebody doesn't come every day. So in some ways, you might have a better estimate if you wait a week, at least in terms of /64s. It's an exaggeration, certainly, if you're using full addresses because they change so often. So I talked about that other stuff down in the weeds. Let's look at those transition technologies like Teredo and Isotap and 6 to 4. Well, all of them are either declining. There's a little bit of anomaly with Teredo, but we're down. This is so far, this is on a log scale, really way down there. So I don't pay much attention to those. I mean, we're really interested in people that are full up native v6 to the web. Now, there are certainly other ways that we can measure it, and we saw a little bit of up and downs in what we were looking at before, but what if we counted the number of ASNs that those active client hosts were within? Well, then we see this sort of steady growth. And that's encouraging. So it suggests that maybe this is a web-based anomaly first that we saw where it was a little drop-off at the end because the number of active ASNs with clients, this isn't the number of active ASNs in the BGP. This is the number of ASNs that have active World Wide Web clients that touch the Akamai platform. So there's a subset of what you see advertised out there that we just never see any activity from. They could be server things, but there's a lot of quiescent v6 prefixes out there. So another way to look at that, and this is the most timely results I have for you, is across those ASNs, how many gains or losses have we had in numbers of active addresses? Well, or maybe 64s here. It means that of the 5,000 some ASNs, almost all of them are steady state for the last 6 months. If you're interested in you're interested in the advancement of v6, this is not particularly good news. There's not a lot of ASNs that are increasing. Although on the left side over there, where I have Comcast labeled, that was one of the biggest gainers. So a lot of v6 come there. And then now again through the Akamai lens, over here on the right side, T-Mobile was one of the ones that dropped the most. I'll explain that it's not actually a drop in IPv6 activity. It's just having to do with our lens that we're looking at it through. So if I zero in on, or look in on some of the gainers, well then you see it's like, this is just in the last 6 months, by the way. Comcast is up there, partly due to an anomaly, but them just changing the way they use the AS numbers to advertise the prefixes. But Deutsche Telekom, TIM Cellular in Brazil, SK Telecom in Korea, Reliance in India. So these are the most recent big networks that are deploying v6 from the window that I have available to see it up to March 17th of this year. If we look at the ones that in my data lost the most, we see T-Mobile, Verizon, AT&T Mobility, and you notice that these are all the ones that we think are the heaviest v6 users, right? These are the mobile carriers. Well, what's running on a mobile carrier? An app, right? So if an app changes its behavior and doesn't come to the Akamai platform as often, it might look like a loss. So I'm just saying those aren't real losses. They're just decreases in our counts if I'd have to wait a longer period of time to measure those uses. and then in a tabular form, like the top 20 or something. So the reason I put this one up is look at the country codes. We're talking about Brazil, Germany, Korea, India, US, Brazil, Japan, France, Brazil again. So activities in different parts of the world. Now that was looking at it all based on different ways of measuring, and I said, remember we saw that graph where there was a dramatic increase in the number of addresses when we looked over a week instead of a day. We went up to 2.82 billion in a week. Well, this is because a lot of clients use temporary privacy addresses and they change their address at least once a day, sometimes very many times a day. I've seen individual client hosts change as much as 100 times in a week. And so what we're going to do instead is to measure this temporally. Let's look at all the addresses that are, for instance, on one particular day. On this day, March 23rd of 2015, we saw 363 million active IPv6 addresses shown there. And of those addresses, let's look at some notion of stability with them. Were they there the previous day? Were they there the day before that? Were they there the day before that? And so of those 363 million, on the day before, only 83.8 million of those are there. Well, that's consistent with the RFC recommendation about changing your ephemeral address or your privacy address every day. And then if we look the day before that, only 24.1 million, 16.4 million, and you play it out like that. So the ones that I've highlighted here in blue, if they were active on the 23rd and these days that were separated by some days, I'm calling those stable addresses. These are addresses that we keep seeing as clients come back to the platform, and it's kind of like the way you think an IPv4 address. So we can separate the stable from the transient addresses, and that's useful, for instance, in monitoring. If I want to do a trace route to them, if I think there's some reputation, maybe these are the ones with all the zeros in it, and they just don't change very often. The next thing we can look at then is like over those sampling every 6 months, we can look at, well, how has the count and the stability changed over time? Well, it hasn't really changed over time. About 96% of the World Wide Web clients are not stable addresses. And that's, again, recommended. That's the privacy addresses and these ephemeral privacy addresses. In the most recent period of time, we're seeing 94%. So you've seen there's a growth, and most of the addresses are these throwaway addresses. You'll never see them come back because they have a big random number in them. We can do the same thing at the /64, right? So the simple model is you get a /64, and then the machine changes, if it wants to, its interface ID within the /64. So you might expect /64s to be stable and the full 128s to be not. But when we play out that same sort of thing that we just did with the counting before, we see that the number of stable /64s drops off as well. This was a surprise to me when we first saw the phenomenon. So that means that the subnet identifiers are sometimes not stable either, instead of just the full addresses. And how does that look over time? Well, we're seeing an increasing number of non-stable /64s, okay? And we'll delve into ways of looking at the addresses spatially to discover why that might be. So at the beginning of the presentation, I showed you a cross-cut version of a tree with the tree rings. The study of tree rings and ages of trees and when things happen is called dendrochronology, and it means branch in time. And if we in IPv6 addresses as well as IPv4 addresses can be expressed in a tree. So here what I'm going to do is build a tree and show you how this notion of studying things as branches as they evolve over time is a really neat way to think about the way IP addresses are structured. So what I've done here is build this base 2 radix tree. Sometimes you hear them called Patricia trees, level compressed trees. And I've punched 5 addresses in there. Those ones showed in solid lines. And then here are specifically the 5 IPv6 addresses that I put in there. 4 of them look like these low number, hand-numbered ones, and one of them is one of those privacy addresses. And what you see this data structure builds out, it's the minimal way that you can represent the decision-making to differentiate those addresses from each other. It happens that in this kind of tree, the parent node is the number of bits at which the 2 addresses differ from each other. So you can imagine, if you're trying to understand a set of addresses, one of the interesting characteristics is at which bit does the address differ from its most adjacent or nearest address. And you call this discriminating prefix length. So you can give me any 2 addresses. All I do is find number of bits in common. The next bit is the discriminating bit. And a router, that's all it needs to know to be able to differentiate the 2 and send the packet appropriately. So it has very much to do with the way routing tables work, although modern routing tables don't use a simple data structure like this. So if I put the trunk on the tree and we look at counting these, we can study the structure of the tree in 2 dimensions just by counting the number of branching at every level. So here we see there's 1 branch at the trunk, there's 2 branches here, there's 3 branches at this level, and there's 5 branches at this level. So if you were given the weird task of saying, characterize a forest of trees that were all 128 units high, which is what v6 addresses are, you could use this as a way to classify them. But that's kind of dissatisfying. Of course, you can scale it even on a slide between 5. But we're talking about looking at hundreds of millions or billions of addresses in a space of 340 trillion possible numbers, right? So you're vastly sparse space. And so now let's develop a visualization method to look at a small set of addresses and show where they are in a vast space. So there's a real tree, and what we're doing is developing this thing we call a multi-resolution aggregate plot. Multi-resolution because we count the number of active prefixes at every level, and we plot them out here as some sort of mass. So if the branching happens low on the tree, it'll be towards the left, the low bits rather in the address. If the branching happens in the middle, it'll be about in the middle of the tree. And if it happens near the top, this would be like an address that ::1 and ::2, the addresses are very near each other. They will branch at the top, and the mass will be deposited over here in this multi-resolution aggregation plot. There's a research paper linked at the end that explains this in detail for people that are interested. But the intuition is that you fell this tree, and it deposits where the addresses differentiate them from each other at those positions. So now I'm going to use this visualization as a way to classify the set of addresses that I'm studying. So here I took 12,000 addresses seen over a week in a Japanese telco, and I pushed them through that algorithm and it come up with this plot. And I'm going to give you a little tour of this to convince you that this is a good discriminator or way to characterize that set of addresses in the way that that network happens to number itself. So what we see in the addresses in set, sample addresses, there's a single bit at which they differ. It looks like subnetting there, and that shows prominently as this little blue spike down there at the bottom. We see that a bunch pile up in the middle, and we see this kind of black steps down from 64 to the right. That's a signature of privacy addressing. If you have a pool of random numbers, in this particular kind of plot, it will show those steps down. On the rightmost, when you have addresses that are very close to each other, it'll happen exactly the other way. It'll step up. And this is like your car's odometer. If you have a bunch of serial numbers packed really close to each other, you'll be counting very quickly with the lowest order ones and slightly less quickly with the next, and it'll pile up that way. So we have a way visually to get an idea of what kind of addresses are in this pool. Now let's look at a different network. A US university with 7,000 active addresses, completely different picture. But we see it's prominently these privacy addresses, if you believe me that those steps down from 64 are evidence of random numbers. And if we look at the example addresses in set, certainly they look like a bunch of privacy addresses. You can see particular phenomenon, like for instance, the RFC specifications for Slack addresses prescribe this universal bit be set to 1 or 0, depending on whether it's globally unique. And you can see evidence of it being set to 0 because we don't know that the random number is globally unique, so they're set that way. If we look at a different network again, this Japanese ISP, a different one, we see a very different scheme, right? And what we see here is that the discrimination between addresses is happening way up in the high bits. I think here in this network, you can't tell just immediately from this that they're using possibly their IPv4 subnet identifiers in the high bits and differentiating it up there. Then they have a run of zeros between 48 and 64. Then you see privacy addresses. One of the biggest networks that'll touch this US mobile carrier, 510 million active addresses. They pile up completely differently again. It's a function of the way they do subnetting in the top half of the address. And then again, we see those steps down, evidence of many privacy addresses in that space. And European ISP. This is the most interesting one that we found and why we think this technique was particularly valuable in classifying. Because remember I told you those steps down are indications of very sparse, possibly random numbers. We see 3 discrete segments of steps down. There's the one from right to left that starts at 64 bits and steps down, privacy addressing. But then we see another little one in the previous 8 bits that has the same thing, and another one something like 12 bits before that. So this looks like they are using random numbers, possibly hashes, in the subnet identifier. And if you do this, it will exaggerate the number of /64s you have in your network. And then the last one, we talked about, people think /64s might identify a host. Here's a network where in a week's time, in 1/56, there was only activity in 1/64, and that was 459,000 active addresses in a week. What if you put in a rate limit or an access control list at the /64 level that affected this? You might be blocking tens of thousands of hosts. Okay, so let's switch to something fun, graphical visualization of the internet. So in the IPv4 internet, John Heidemann and his students came up with this visual heat map of the v4 address space. Each one of the pixels in it is a /24. They try to ping them, and they can determine whether it's active or not, and then they color them according to the number of responding hosts within it. Unfortunately, in the v4 space, because you've got 340 trillion addresses, you can't do a two-dimensional map. There's no right size. Well, in fact, it would actually have to be a /24 as well, and a /24 in the v6 space is awfully large. So what we developed instead is something called the classified tree map. So we're going to take the classifications we used earlier about the temporal and spatial aspects of the address and use those to color and position the blocks here. So what we're doing is sizing each of the rectangles. Let's use an example before we go into the demo. Down in the right-hand corner, it says Akamai Technologies and the AS number there, and that purple block there are the prefixes that we advertise. Now here, each one of the individual little rectangles is a discrete advertised BGP prefix, but they're sized according to the number of possible addresses there could be in there. Well, that's pretty meaningless in v6 because you never fill up a prefix. They're just astronomically huge. But one way to visualize relatively who's advertising the most space. The other ones you see up here is CenturyLink. There's Sprint Wireless is in yellow there. In the low middle, there's an orange. That's KDDI in Japan. Verizon Wireless is kind of in that kind of dark yellow in the middle there. So we'll go into a demo right now where I'll show you how we can explore the active IPv6 space using this technique. So I'm going to bring up Safari here and maximize it and show you the same thing. Oop. All right, sorry about that. Okay, so what we have here is that exact same visualization based on the log-base 2 size of the BGP prefixes advertised. And what we can do here is choose other metrics. Like the first thing, let's say you want to see in the world, from our perspective, who's got the most active v6 addresses. Let's choose active addresses. And the visualization will morph into this. So let's see, here's some of the heaviest hitters as clients in the world. Verizon Wireless over here on the right, AT&T in brown up here, Comcast right here, Deutsche Telekom in this kind of salmon colored right here, KDDI, T-Mobile, here's Telefonica is in here, GVT, all these kind of guys. Now let's look at this. So this is counting at the full number of addresses, but remember I said this isn't necessarily respecting the entire number of users. Let's look at something like the number of active /64 prefixes. So let's have the visualization morph into that. And now Verizon looks even more prominent. So if it were the case that you could estimate the number of users based on /64 counts, you would think that Verizon was the biggest. They certainly are big, but we think in the mobile carriers they use dynamic components in some of their subnet identifiers, so those counts don't necessarily respect those particular, they're not necessarily a good estimator of the number of users there. Now, we talked about this sort of stability. Well, which networks have the most stable addresses where they're not using these ephemeral things? Let's switch to saying, well, show us the most stable addresses. And these are the networks that have the most stable addresses, Comcast, AT&T, Verizon. And remember, this can just be based on a host deciding to use that particular mechanism to choose its interface identifier. Which have the most transient /64s. So those kind of, remember I said there's these weird /64s that don't come back to us. They must be doing something unusual up in that part of it. And look, you see it's all the mobile carriers. There's probably pieces of gear out there that decide to allocate, they have an algorithm for allocating the /64s, and then they push them down the user equipment, and the user equipment takes it from there. Oops. So let's switch to some of the percent transient /64s. Which networks have the most transient addresses? Again, another visualization of the same thing. Which ones have something like the most stable UI64s? Which ones are ostensibly exposing the brand of their Ethernet NIC? Well, that's these networks. Hughes Networks, the satellite carrier, I think they must have some customer premise equipment or something that uses the UI64 address. You see people in Comcast and AT&T doing it. If you're interested in doing a risk assessment of potential, vulnerabilities to scanning from outside, those might be ones you want to pay attention to. Now let's look at things like dense 112 addresses. Which networks have the most addresses that are near in 1/112 to other addresses? So that if they're very near, right, and someone discovers one of the addresses, they could scan nearby and detect them. These are the networks that just happen to have the most addresses in dense 112s. What about dense 112 prefixes? Now it morphs to here. We can do something like, actually I wanted to visit because I think our hosts are in here, right over here, Facebook on the left. So Facebook, now as a client, right, as a client of the Akamai platform, Facebook looks like one of the networks that has most of its addresses packed in /112s. It doesn't mean they're using /112s in their IGP. It means that they're within that distance of each other, those addresses. And we can ask things like, which has the most % stable addresses? Again, these are ones where the reputation would be durable over time because they seem not to change their addresses. And then maybe another way to look at it. So remember we talked about, we were back at stable addresses. Straight up active addresses. On the bottom here, I have this slider. And in that thing that we were showing before about the MRA plot, we were talking about at every possible prefix length, how many active prefixes do you see there? That means we can take at any 2 points, like at 128 over here, we can take the count there and express it as a ratio of the count at another length. So the number of active addresses is the number of active /128s over the /0, which is 1. And that's why you get that count. But I could do something like slide this slider over here and say, give me the ratio of how many active /128s are over the 112s. And now these regions of this plot will be sized according to which ones have the most addresses in /112s. And now you can see Facebook very prominently, Cloudflare very prominently. So in this case, now remember, these are clients of the Akamai platform. I have no visibility to what they're doing besides that, only when they come to us. So this is, for instance, another CDN coming to us for content. And a customer could potentially arrange that. Perhaps they're using us as origin. Perhaps they're determining, what's going on in our network. We have no idea. But that's where some of those are. So I'm going to come back to the presentation. And play from current slide. So I talked about this thing about tree rings and stuff. So the technique about the spatiotemporal technique, I'm calling it dendrochronology. Dendra, plural in Latin for branches, and like the branches of the tree we showed, and chronology, just looking at things over time. Now, we just have a few minutes left, so I'm going to give you a very quick look at what you can do operationally when you study the addresses this way. So we looked at before a way that straight up statelessly, you can just look at addresses using the attr6 tool, and it tells you something about them. Now we looked very statefully, we looked over time, and we looked in over space at those addresses. And so here I'm going to show you a technique that we're using to do a kind of prefix intelligence. At what level, if I asked you, what level should I pin up an ACL to block a particular bad actor in the v6 space, here's one way you could make a decision. So what we have here in green is the /64 prefix. This is just v6 addresses with the colon taken out so that they're easy to manipulate with text utilities. And in green there, you're seeing that they're all in the same /64. So this is 80 addresses all in the same /64. So maybe if I pin up a /64, it's going to affect all 80 of them. Do I want to do that or not? So what I can do is look at the /64 prefix, the set of interface identifiers, and somehow statistically analyze them. The discriminating prefix length in the third column there is that thing I was telling you about. At which bit do they differ? And you can see these discriminating prefix lengths are very high. That's a spatial characteristic of the addresses. You know that this is dense address space because the discriminating prefix length is high. And then in the last column, we show how many days stable it is because it's interesting to know, right? You would want to know if you're going to pin up an ACL, how long might it be good for? Well, is that address ephemeral and going to disappear tomorrow? So we do a deep analysis on here. There's a presentation that we have in an IETF slideshow that I can give to you if you're interested in the details. But basically, we do a deep analysis on there, look at the median, the distributions, the different values, and we can come up and decide that in this particular network, it looks like the slack probability is 0. I don't think this is a slack network. I don't think the hosts are numbering themselves. So the host itself does not have the liberty to change its address. If the host doesn't have the liberty to change its address, then /128 is a really good prefix length to use for a rate limit or an ACL. If we look at the more typical case, in a set of privacy addresses, here's one /64, then in a week's time we see 1,600 privacy addresses. What are you going to do if one of the bad actors is in this prefix? Well, you run the same sort of analysis and we say, you know what, this came up as slack probable 90% by my algorithm. And we're saying, because we think slack is being used in there, means any host in that prefix has the liberty to change its address to any other address in the prefix. So if I'm going to pin up an ACL, I better use a /64. So that's one practical application of doing this kind of analysis. So a couple of takeaways. I said before, IP geolocation, if any of you are interested in partnering or collaborating with us about improving geolocation in v6 space, that's one of the impediments now for people putting content up, by the way, in v6. You have to have good geolocation to be able to restrict content by country, to be able to do targeted advertising and things. So if we can improve that, we're going to help the v6 effort. It changes client rep by the example that I showed you there in terms of just how long they live. It changes threat mitigation. Some of these other things, we've made some progress on this. It's relevant to most of our engineering work. It's different than the way you were thinking before. I don't mean to make it sound too complex. It's differently complex than running a v4 internet with more users than addresses, but it's also complex. And so I said we made some progress here. Some of this stuff is open. You guys can implement it if you want, or we can talk about collaborating and improving the situation. So thanks a lot. I have a couple links up here that are important if you're interested in following up on this. The research paper that my colleague Arthur Berger and I wrote is linked at the top. We also released all those counts that are used to produce those graphs. So if you want some real data, you noticed in my graphs I didn't have the access labels missing. These are real numbers. So they're not sampled, they're real numbers of what we see. There's some data up there. And then at the bottom, sort of a plug for my research group in the IRTF. Measurement analysis for protocols. We do this kind of work. What kind of measurements do you need to do on the real internet to improve operations and to improve protocol design? So thanks.